Alright guys, so we are diving into 5.2 for the day, and the goal of this video, we're really going to be only focusing on is simply defining the Riemann sum and kind of showing its relationship as to why the Riemann sum is in fact a definition of our definite integrals. Okay? So let's kind of recap for a sec. In the last section, in the last videos, we started looking at how to find the area under a curve. That's kind of what's represented in this diagram on over here. So what we ended up saying is if we wanted to find the area under a particular curve, we would partition or cut it or divide it, a variety of amounts. All right, and obviously we ended up saying is that the more partitions, the more cuts that you have, the more stronger of an approximation you're going to have of the area under a curve. And so we sat there and we made a bunch of rectangles, and we decided that we're going to find the area of these rectangles and then add them all up, and then boom, that was going to be our estimation or our approximation for the area under the particular curve. In this case, our little function that's in blue over here. Okay, and when you think about adding all of them up, that is called a summation. All right, that's called a summation. And what we are going to look into is one of the most famous summation notations, which is called the Riemann sum. And that's what you see on the screen right now is our Riemann sum. Okay? So first off, where does his name come from? Riemann. His name is Bernard Riemann. He is a mathematician that had a lot of different contributions to calculus itself. But he started kind of coming to the conclusion that there has to be something that kind of wraps up this concept of area under a curve. And he started kind of putting it into a summation notation formula. And so if you are unfamiliar with summation notation, let's talk about this. This big E funky looking thing that we see on over here, this represents sigma, and this represents the sum of, alright? So sigma stands for the sum of. I'm going to write this on over here if we need to. So sigma, we'll just put sum of, okay? And then there's parts to the sigma notation or the summation notation. Where you see K, K is called our index. And that's kind of the beginning point for whatever the x value is. So you see inside that function, x sub k minus 1. Alright, well you're starting at x sub k minus 1, which is 1 minus 1 is 0. That's our starting point, okay? And then as we kind of dive a little bit further into it, you also are going to see that number n that is going to be on top. And that's our ending number. N is kind of our end number. Alright, so if I'm starting at 1, I'm ending at whatever number n is for this summation, okay? So I have my starting point, and then let's say n is 10. I would do the sum of this particular function, starting at k equals 1, ending at n equals 10, okay? Hopefully that makes sense. So I just kind of want to take some time and to explain what all of this madness, if you've never seen this, looks like, okay? And so inside of this summation notation, you see a function, and it represents f of x sub k minus 1 times delta x. Now this specifically is our summation notation for the definite integral as a way to find the area under the curve, okay? Now, we haven't gotten to an example of how to use this yet. Our goal for this is just simply to define and explain where this comes from, all right? And so what basically ended up happening is Bernard Riemann started to think about, well, as I am getting more and more rectangles underneath my curve, I'm just making more rectangles, more rectangles, more rectangles, more rectangles. Now, obviously, the rectangles are getting smarter, and I want to get as many little rectangles in there because the more I get, the more strong of an approximation I'm going to have. And so what he ended up saying is that, well, as I get more and more rectangles, that is when n, our n number, is coming and approaching infinity. And so what he ended up saying is that if I take this limit of this summation, and so that's what I'm going to write here. He said if I'm going to take the limit as n approaches infinity of this summation, what I am going to get is I'm going to get the exact representation of the area under the curve. And that's going to lead us into the definite integral. And so what this ends up representing is how we're going to use it a little bit more so, is that the limit as n approaches infinity, excuse me. So this is going to lead us into what we know as the definite integral. And we write this as the integral from a to b, all right? It's our starting point to our ending point for our interval that we are looking into. Of, in this case, f of x times dx, okay? So dx represents that differential because delta x is the change from b minus a divided by n, where n is the number of partitions that we took. Well, as we're approaching infinity, n is becoming infinite. And so what dx represents is a differential, all right, of the function itself, all right? So it kind of represents that infinitely many changes of x. It's really what dx is supposed to represent there, infinitely many changes of x, okay? And so this kind of is where we get what our next step is going to be in actually evaluating integrals themselves, okay? So that kind of wraps up this video. Just wanted a simple definition and what some of this notation actually represents and what it looks like. In the next video, we got some couple examples of how we're going to use the following information.